thank you. It's a great pleasure to be here in Tenerife. I've never been to Tenerife before. I enjoyed the flight here. I happened to, by luck, because I had no choice of getting assigned seats, to be able to sit on the right side and actually see the Rock of Gibraltar and the Straits of Gibraltar on the way here, so that was a delight. Okay, this is some of our scenes from Canada, from on top of Mount Temple, overlooking Moraine Lake. Okay, I changed the title a little bit. I don't know whether this is getting outside my comfort zone or maybe getting into areas I love to speculate on. Bill, you have a question?
Is that capital C or lowercase c?
For Cosmology, yeah, this will be it. I will be getting into capital C. A good part will be lowercase c, but I will get into capital C. Okay, so I broadened it a little bit, making it a bit more philosophical, with the danger that I'm very naive in philosophy compared to the philosophers here. So anyway, you can correct me later on this. So I'm saying in cosmology, now this would be a lowercase c, we would like to explain our observations and predict future observations from theories of the entire universe. So these cosmological theories make ontological assumptions of what entities exist and what their properties and relationships are. One must also make epistemological assumptions or meta-theories of how you can test these, and that's what I will discuss. Well, first let me lay my cards on the table. I am an evangelical Christian, and I do believe that beside the universe there's God, and I'll talk a little bit about this top level later. I'm mostly going to focus on this middle section, our universe or multiverse, but then I have sort of three aspects of God that I sort of summarize there, which are very, very crudely analogous to the three persons of the Trinity, but they're not to be identified with that. Okay, but for the main part of the talk, I'm going to be talking about the section in the middle, our universe or multiverse, and in that, I'm taking observations as conscious perceptions, first-person subjective sentient experiences, and then I'm assuming that for each one of those, there's a positive quantum operator, and then there's a quantum state for the universe that gives measures for observations as the expectation values of operators for the observations. So this central section is basically my assumed ontology for the world. And you might notice it doesn't even say space-time is basic. I think it's kind of derived or Hamiltonian or any such thing, but it's just this stuff. Later, at the latter part of the talk, I'll get a bit of an argument for getting a bit of that, but my main reason for believing in that is I think the historical evidence for the life, teaching, death, and resurrection of Jesus, and because of what he said, I believe in some of these things. This last is pure speculation, but I'll throw it in. Okay, so let's go to some of my assumed epistemology. I'll define a complete theory of the universe as one that completely defines or specifies all properties of the universe. So I shall assume that an observer who could observe all properties of the universe and has unlimited reasoning power could deduce a unique complete theory for that universe, if he could observe everything. Now this would, of course, I have to imagine an observer outside the universe because it can't be limited by quantum mechanics. It has to be some godlike observer, I mean, maybe some angel that God created that could really see everything about the universe. I'm also counting equivalent complete descriptions of the theory as the same theory. So, you know, there's often two different formulations of a description of something that are complete, but if they're equivalent, I'll just regard it as the same theory. Now, there's lots of complications in epistemology. I don't know that much about it, but it seems like a lot of the complications arise from limited reasoning power of humans. So for this talk, for simplicity, I'll just sweep that under the rug, and I'll consider idealized cases in which observations are limited, but reasoning powers are not. So to get me extremely idealized, I'm imagining going to, you know, the far distant future and, well, probably beyond our universe. So, but despite this idealization, a limited observation does not imply a unique complete theory of the universe. If the observer just sees part of the universe, no matter how good his reasoning power, there's this problem of underdetermination, that there could be many theories that fit that. And furthermore, the idealized observer cannot deduce the posterior probabilities or credences of different theories fitting his or her partial observation without making subjective choices for the prior probabilities of these different theories. We can be guided by Occam's razor, but I don't think there's an absolutely preferred prior probabilities for the theories. So I'm going to take a Bayesian analysis. I'll consider a theory, T sub I, for each possible observation observation, O for observation, subscript K for which one, then I'm assuming that it gives a probability for that observation. Now, if we assign subjective prior probabilities for the theories, presumably higher by Occam's razor, so I mean, I don't regard them as completely, arbitrary. I think as scientists or just as humans, we would prefer simpler theories or we give them higher credence, but exactly how you do that is sort of up for grabs. And then if we use the observation, okay, to test the theory, then the probability of the observation given in the theory is then, for that particular observation used to test the theory, is then called the likelihood of the theory. It's kind of a very bad word, but anyway, that's the standard thing. And by Bayes' theorem, we can calculate the posterior probability of the theory as the product of the prior probability of the theory times the likelihood and then normalized, but divided by that over all possible theories. So what we would like to do is to get the posterior probability as high as possible. And we have this trade-off. We have to, by choosing a simple theory, which might give high prior probabilities, and also give a good statistical fit to observations, or high likelihood. So now we have the first challenge, is that I said that a complete theory should completely specify all properties of the universe. So you might think the complete theory in some sense determines it. I mean, it describes it. I'm not saying it causally determines it, but it completely describes it. So you might think, well, there's no room for a probability there. I mean, indeed, there's no room for chance or uncertainty or randomness. So you might think that all the probabilities would be either 0 or 1. If the universe has this property, the probability is 1 that it has the property. If it doesn't have the property, the probability is 0. Well, if you use those sort of probabilities in this thing, the likelihoods would be either 0 or 1. Well, then the posterior probabilities of the theories would just be proportional to the prior probabilities of the theories that do have that property, that give the probability 1. But even though I'm a theorist, I do think observation should play an important role in science. So I think that the probability is that observations ought to take a bigger role in this. We ought to be able to somehow, even if we had a complete theory, to be able to get probabilities between 0 and 1 for specific observations. So what I'm going to say is I'm assuming the theories I'm talking about can give normalizable measures for observations. Then these normalized measures, if they're normalized, they can be interpreted as likelihoods that can vary between 0 and 1. So these measures I'm taking as real ontological aspects of the world if the theory is correct. So they're not just measures that we come up with out of a hat. I mean, we can make guesses for what they are. We can make different theories of what they might be, but I'm interpreting them, these measures, as being real objective facts about the universe. Facts, of course, that we don't know. So there's the epistemology. Now, in a classical theory, if you had the system is a trajectory in some phase space, the measure could be functionals of the phase space trajectory. I mean, one candidate might be that an observation might correspond to some region in the phase space, and the measure could be the time that the system spins in going through this region. And in the quantum theory, they could be certain functionals of the quantum state, or maps from the quantum state to non-negative numbers. And later you'll see all advocate linear maps so that the measures are expectation values of operators. So, okay, now let me give another argument why the probability against likelihoods all 0 or 1 are close to that. And this, by the way, is a bit of criticism of the particular approach that Jim Hartle was talking about, because if you have a highly inflating unit, if you have eternal inflation, so the universe gets very, very big, almost all observations will have an existence probability, the P sub E of near unity. So I'm proposing a different approach. I'm saying it doesn't seem, in my view, to work to use existence probabilities if a huge number of them are all very close to 1. Okay, so now if the theory leads to the definite existence of more than one observation, you might be able to say that it's 1 for all those observations. That would give unit likelihood for any theory predicting the definite existence. But then that would mean that, of course, you could produce a theory to give unit likelihood no matter what the observation turns out, just by saying the theory predicts that all possible observations actually occur. But that seems too cheap. I mean, it's supposedly explaining everything, but I'd say it actually explains nothing. It says everything exists, but it doesn't give a good explanation of the particular thing we see. So I'm proposing the normalization principle, or you could say it's a meta-theory, that each theory give normalized probabilities for the different possible observations. So their existence is not mutually exclusive. I can have an observation, you can have an observation. The existence is not mutually exclusive, but the observation as an observation is mutually exclusive. I mean, my present observation is presumably different from your present observation. So the observations are mutually exclusive, so if I can assign normalized probabilities to them. So I'm proposing that the sum of these over all observations should be unity. And that's different from other approaches such as Jim's. Okay, let me describe this in a somewhat different way. Suppose we think of this as sort of a contest that different theorists are trying to propose. They're in a contest to try to come up with the best theories. So you could view this as a contest, theorems, but then you're only given finite resources in solving this. So I'm proposing that theorists should only be given a unit probabilistic resource to divide at will for each theory. And then others can judge the theory by assigning prior probabilities to the theory based on the simplicity of the theories. So then normalizing the products of the priors and the probabilities the theories assigned to the observation used to test the theory then gives the posterior probability of the theories. So I'm saying for this to be a fair contest, each theory should be allowed a unit probability to distribute among the observations predicted by the theory. So now, of course, if the theorists cheat and they give unnormalized probabilities, such as assigning probabilities near 1 for more than one observation, of course, the judges could compensate for that by just assigning correspondingly lower priors. They say, you know, this is not a good... I guess what I'm saying is, you know, if a person has theory A and the probabilities or observations add up to 1 and somebody else says, I have a better theory B. In my theory, all the probabilities are just much higher. You know, maybe none of them exceed 1, but they're all higher than theory A. And I'm just saying that seems like a cheat, and so if the theorists cheat this way, I think the judges should compensate by assigning correspondingly lower prior probabilities for it. However, I'm saying that it would give a more clear division between prior probabilities for the theories and likelihoods if the theorists obeyed the proposed rules and normalized the observational probabilities for each theory so that they sum to 1. So if you do that, then there's a trade-off between prior probabilities and likelihoods. So you have the prior probabilities for the theories. These are intrinsic possibilities. And remember, the theory here includes not just the quantum state, the dynamics, and so on. It also includes this measure. It also includes the measure for observation. That's part of the theory in my way of putting it, which I think differs a bit from the previous. I mean, each theory describes a different possible world. And so in my way of taking the different measures on observations, if the measure is different, that's a different world. So I think that differs from the outlook of the previous talk, if I understood it right. Okay, then there's the conditional probabilities for observations, these likelihoods, and then the posterior ones are this normalized. So prior probabilities are subjective, but we do usually assign it higher for simpler theories. So I personally, well, I have an ad hoc way that if I could put them in order, if suppose there's a countably infinite number of possible theories, that I will give non-zero probability to, then I might take the simplest theory of having a prior probability of a half, the next one a fourth, the next one an eighth, and so on. So 2 to the minus n for the nth theory. So the simplest theory that I can think of is that nothing exists, or nothing concrete. I mean, maybe math theorems exist, the Platonic math worlds. So this is like what Jim Holt was talking about last night. Is there a reason for the universe to exist or not? Well, I'd put the prior probability. This really means absolutely prior. I mean, it's supposed to mean prior to all possible observations. So it's not including any facts I know before. So I don't do any updating of things because my priors are all really prior. So I might assign that the prior probability of a half, say for that, to put the largest for that. But of course, if the observations are concrete, they're contingent, they're not logically necessary. So they wouldn't exist in this theory, and so the probability of our observation, of any observation, would be 0. So then the posterior probability would also be 0. Now the next simplest theory I can think of is that everything exists. Well, you may have to refine that a bit more if you want to say that all possible observations exist, and if you say all observations exist with equal probability, Well, surely there is an infinite number of possible observations, logically possible, because we're considering all possible worlds and so on. So then the probability of that would be 1 divided by the number of observations, so that would be 0. So if you normalize, you get 0. So this is my way of ruling out Nozick and David Lewis's proposal. I mean, I don't know if they made it really precise enough to talk about probabilities of observation. But if you try to extend it by saying that all observations have equal probability, I would say that that again leads to 0 likelihood. So that's the way I rule out that theory. Now, the other extreme would be a maximum likelihood theory. So that would give the probability of unity for the observation used to test the theory. And of course, if it's normalized to 1, that means the probability has to be 0 for all other observations. So if I really believe this theory, which I don't, then I would say my present observation exists, but none of yours exist. I'd also have to say that I have memories, but they don't really correspond to any actual observation I had before. I was never conscious before now. It's just at the moment I have mine. Well, my present observation is rather complex. I see lots of people here and lots of detail, and I remember things. And there's just a lot of detail in that. I think it would require a very complex theory to predict exactly my present observation and no others. So I think that would, I don't know how to calculate it, but I think that would require a theory that would be very complex that I would assign a very tiny prior probability to. So I think there's a trade-off between the prior probabilities and the likelihoods. Definitely, maximum likelihood is just not a good procedure, but neither is the highest prior probability a good procedure. So the measure problem in cosmology is how to obtain probabilities for observations from the quantum state of the universe. So it's particularly a problem when eternal inflation leads to a universe of unbounded size, so there's apparently infinitely many realizations or occurrences of observations of each of many different kinds, tending to make the ratio ambiguous, as the previous pair of speakers spoke. And of course, it can be very difficult because you can have two parts of the universe that have different constants. And even if you could use some metric or something to try to say, well, we'll go out to some finite distance here and some finite distance there, do you really use the same distance when all the constants of physics are quite different in the two things? It's a big problem to know how to do that. The measure problem seems to be related to the measurement problem in quantum theory, which, well, I'm not sure what's the best way to state it, but it may be how to relate quantum reality to observations that appear to be much more classical. So an approach I shall take, as I've mentioned, is that I'm going to assume observations are fundamentally conscious perceptions or sentient experiences. I use those two phrases interchangeably. Each perception being all that one is consciously aware of at once. And I take that as a really fundamental thing. I can't define it in terms of anything simpler. I can sort of point to it by using these words. But I think it is a fundamental, and it's, as many people have said, it's the thing that we're most sure of. I'm most sure that I'm actually aware of something. So, okay, so I'm going to take an Everettian view, well, in the sense that I believe the wave function never collapses, that in the Heisenberg picture there's one quantum state for the universe. So there's one fixed quantum state, and it could be a multiverse. I'm not arguing for or against it, but I can maybe say some words later, but I probably don't have time. So I'm assuming instead of many different worlds or many branching things, what the many of are many existing observations or sentient experiences, not only yours and mine at the present, but ones in the past, but also in what crudely might be talked about as different branches. But I don't need to talk about branches of the wave function. All I really want to talk about are the observations. So for simplicity, I mean, it could be a continuum, but for Bayesian analysis, it would be simpler if it was a discrete set. So I'm going to assume there's a countable discrete set of observations, and I'm assuming the theory really gives objective measure for this thing. This is something that the theory produces, and I'm assuming that this is a real fact about the world, and we want to try to discover that, as the quote from Max Tegmark was that the previous speakers wrote. I'm taking the same attitude. There's some real measure we'd like to learn. We don't know what it is. And so I'm assuming different theories give different values, different measures for that. And I'm assuming that, for simplicity, let's assume that you've normalized it to unity, so I can just interpret these directly as probabilities. So I'm going to interpret the normalized measure for the observation that each theory gives as the probability of that observation given the theory. So, and if you use this observation to test the theory, that's then the likelihood of the theory. So, now, the universe we believe is fundamentally quantum. A classical approximation may be good, but it's fundamentally quantum. So I'm going to tie it to quantum theory. And the map from the quantum state to the measures for observations could be nonlinear. However, as a working hypothesis, I'm going to assume a linear relationship. This is indeed, in fact, contrary to what you get if you apply decoherent histories, because which histories decohere depends sort of nonlinearly on the quantum state. So I think you don't get linear relations in that, and in some of the things I think that Sean Carroll has proposed about eliminating Boltzmann brains, I think he's basically assuming it's something nonlinear in the quantum state. I don't have a strong, I guess if I use a different one of Sean Carroll's papers, you might say that the linear one is the only rational one, but I won't go that extreme. But it does seem to be fairly, well, it seems to be simpler to say it's linear. So I'm going to favor that unless I see reasons otherwise. Okay, so I've called this in a technical paper that's on the web, long paper, 64 pages. I never found a place to publish it without doing major revisions that I didn't have time to do. In sensible quantum mechanics. And I've also, in a paper for lay people, or I've called it mindless sensationalism in one paper, because it proposes that what's fundamental is not minds. So it's not quite the same as the many minds theory. It's many conscious perceptions. And anyway, and if you crudely call these sensations just to make a sensational title, then you get mindless sensationalism. But you know, by conscious perceptions, I don't mean just immediate sensations. I include memories, the fact that as I look at you, I can have memories of having seen and talked with you at earlier at this meeting or previous meetings and so on. So there's a lot of other things besides sensations in here. Okay, so in other words, the measure, I didn't put a subscript for the theory. It's going to depend on the theory. So I could put a subscript for the theory, but for simplicity I won't. It's given by the expectation value of this operator. And this is just the sigma represents the quantum state, and it's just saying that it's a functional that maps operators to complex numbers, and I'll assume this is a positive operator, so it maps it onto, or at least a non-negative operator, so it will wrap onto the real numbers. Okay, so that's the quantum state, that's a non-negative awareness operator, so-called, well, that's my term for it. The quantum state could be a pure state, could be a mixed state given by density matrix or C-star algebra state. And then these awareness operators are these things. So all that is supposed to be in the theory. The theory is not just the dynamics, which I might say is, well, the algebra of all the operators. And it's not just the quantum state. That was a great advance that Hartley Hawking did to say that we really need a quantum state. I think that was a very important conceptual advance, and I greatly admire them for it, even though I'm a little bit skeptical of the precise details of that state. But I'm saying that we need another thing, which is the map from the quantum state to the probabilities of observations. And I'm proposing that it's a linear map. It's given by expectation values of operators. That's a formalism. I don't have a complete theory because I don't know in detail what the operators are. Okay, I think I'm going to have to skip over most of this, but I have a number of papers where I'm arguing that at least for first-person probabilities, the Born rule doesn't work. I'm not necessarily disagreeing with Jim that for third-person things, then you could use it. I'm saying for first-person probabilities, I'm arguing it doesn't work. In other words, taking Born's rule, I'm making it a specific mathematical form of taking the probability to be the expectation value of a projection operator. So that's if you multiply two together, you get the same one back. If it's the same, if it's different, you get 0. So that would be the Born rule thing. And it works. It would work when you knew where the observer is within the quantum state, but it does not work in a universe large enough that there can be identical copies of the observer at different locations, since then the observer does not know uniquely the location or what the projection operators are. So I think I'm going to sort of rush through this. If you have two copies of the observer and maybe they're going to measure something and maybe near one of them there's a spin up and the other there's a spin down, and they don't yet know what it is, but otherwise they can't tell the difference between them, then you'd say, well, if you're really uncertain, you'd like a probability to be between what this guy would get and this guy would get. And if the observer is not certain to be at either B or C, and if the probability if you were at B is this, and that's less than that, without loss of generality, you just choose B and C in the right order, then you should have that. But there's no state-independent projection operator that gives this for all possible quantum states. In other words, I'm supposing you're supposed to fix the operators first, and then you're allowed to consider different states. So there's an open set of states that give expectation values that are not positively weighted means of these, and so the Born's rule doesn't work. And then I gave an example, but I think we'll have to skip over this, where the one guy, in this component of the wave function, one of them sees 1 and the other 2, and in the other one, the first guy sees 2 and the other 1, and then you can get these things, and then you can say, well, in this case, because there's only 2 dimensions here, it's a toy model, and the projection operators have to be rank 1, and if you then go through this, you can say that, well, if the state happened to be the eigenstate of the projection operator, you'd get a probability 1, or otherwise you get 0. And that's what you could get if you chose the state appropriately, and those are not positively weighted means of these 2 numbers for any choice of this. So I'll leave you to read my papers because I'm going through this a bit too fast. Okay, so I'm saying that these operators whose expectation values give measures of conscious perceptions in a big universe, doesn't have to be infinitely big, but big enough that there can be copies of the observer. They can't just be projection operators. So then, but they could be, I don't know if they are, but they could be weighted sums or integrals over space-time of localized projection operators at locations schematically denoted by x. I'm not being very precise here, but, and there may be difficulties of infinities not only if the space-time is infinite, but also you might say, well, we should allow the observation to be, at any orientation or any boosted frame. In other words, I guess I'm saying that if my present observation is produced by my present brain state, presumably that same observation would be produced if the same brain state existed somewhere else in the universe. Well, and it also should be even if it's moving at some velocity and so on. So there's some sort of integral over space-time and maybe over the Lorentz group. And there's technical problems with that, of course, because the Lorentz group's non-compact. So I don't know, how to really do this. But okay, let me turn a little bit to the Boltzmann Brain problem. If you have local quantum field theory, if you have a definite, and let's say for the sake that you have definite globally hyperbolic space-time, then any positive localized operator, such as a localized projection operator, will have strictly positive expectation value at any non-pathological quantum state. So it's like if you look at something localized even in the vacuum state, you're going to get some non-zero value. In other words, suppose you ask the projection operator onto some non-zero charge in some region in Minkowski space-time. Well, that's going to give, if it's a localized region, doesn't include the whole Minkowski space, that can give a positive probability of having charge there because there could be a fluctuation with a positive charge here and a negative charge somewhere else for this moment. So, okay, so if what we do to get the measure for a particular observation, if you integrate this positive localized operator with uniform weight, uniform weight over the space-time with an infinite Fourier volume, then it'll give an awareness value with an infinite expectation value. So you'd have to regularize it. Now, if you said, well, we'll just take it up to some cutoff, we'll use the uniform thing and take it up to some cutoff time, then for a universe that continues forever with the 3 volume that's bounded below by a positive value, then almost all of the space-time is arbitrarily far up here when TC goes very big. And so the integrals will be dominated by times of the same order of magnitude as the cutoff time. So if at late times the probability per Fourier volume drops very low for ordinary observers, if it's hard for us to exist after the stars burn out, for example, then most of the measure for observations will be contributed by these thermal or vacuum fluctuations, so-called Boltzmann brains. So the Boltzmann brains would then dominate the measure for the observations. Well, you might say, what's the problem? Can we get rid of it by just saying, well, we'll put a zero graphic distribution so we're not Boltzmann brains? Okay, so you might say, so what? Couldn't it be our observations are ordinary observers? Or couldn't it be someone else might say, well, maybe we really are Boltzmann brains. But my argument from it, I don't have to invoke any other principles other than just using this Bayesian analysis. I'm saying that since Boltzmann brain, it's admittedly a crude argument, but I think it seems pretty robust. Since Boltzmann brain observations are produced mainly by thermal or vacuum fluctuations, it would be expected that only a very tiny fraction of them would be for observations so ordered as ours are. I mean, it would be extremely unusual for a Boltzmann brain to have have part of its present experience of seeing faces that I recognize as being correlated with memories that I have. I mean, it would just be very unusual for that to happen. So I think that would be a very tiny fraction of it. So if you take that very tiny fraction of the Boltzmann brains plus the even smaller fraction of ordinary observer observations in comparison with the dominant disordered Boltzmann brains, that is, assuming the Boltzmann brains do, then that would be a very tiny fraction of the measure of all observations. So when you follow my prescription or my principle that I'm saying to normalize the probabilities of observations, then the probability of our observation would be highly diluted by the very many Boltzmann brain things. So that would mean that these theories in which Boltzmann brains dominate would give us very low likelihoods for ours. So that's the reason that I think those theories would then tend to have low posterior probabilities, unless you just said you put almost all the prior probability on them. If you allow for other theories and you give them priors that aren't exponentially tiny for other theories, there could be alternative theories in which you put in some assumption about the measure that makes it so Boltzmann brains don't dominate. So if these alternative theories do not have prior probabilities that are too small, and they'd have to be exponentially small, then the alternative theories would dominate. So in other words, we would be led in the end to give the highest posterior probabilities to theories in which Boltzmann brains don't dominate. And I think we can do it just by Bayesian reasoning. We don't have to invoke some other thing that we assume that our observations are veridical or that we assume we're not diluted. We can just do it by this Bayesian analysis, assuming we really do normalize the probabilities of observations. Okay, so now another way of saying it, the Boltzmann brain domination, which is predicted by many simple extensions of current theories, for example, if these awareness operators or their equivalent are obtained by uniform integration over space-time up to some cutoff that is then taken to infinity, they give a reductio ad absurdum of these theories, making the likelihoods very small. So surely there are alternative theories that avoid Boltzmann brain domination without such a cost and complexity that their prior probabilities would be decreased so much as the gain in likelihoods. So anyway, the Boltzmann brain problem is analogous to the ultraviolet catastrophe that physicists then did not believe an ideal black body in thermal equilibrium would really emit infinite power, and similarly, virtually all of us that I've talked to now don't believe that the Boltzmann brain problems really dominate. Okay, then I may have to skip over this. There's some stuff about volume weighting versus volume averaging. I have some proposals of how you could try to ameliorate the Boltzmann brain problem by instead of summing up over these things, over all things, you look at the density of observations on the different hypersurfaces. And then, well, there's still something else you need because of the time. Even if you took the density, if the Boltzmann brain density goes to a constant, very, very tiny constant, if the universe lasted for an infinite time, you'd still get another divergence. So I propose something called Agnesi weighting, use this curve from the Witch of Agnesi, 1 over 1 plus t squared. So, that's a proposal. It seems to fit observations, but it is ad hoc. So I don't think the prior probability for it's very high. Now, let me near the end raise the thing. So I was advocating when we do science, we use this Bayesian analysis, and we assign prior probabilities based on their simplicity, but then we have to weight them by the likelihoods. And in the end, we get a theory. I mean, we don't have the complete theory yet. Maybe it's superstring theory. Maybe it's with this quantum state that's some modification of the Hartle-Hawking thing. And then there's this whole business about what these awareness operators are. But in the end, we don't get a theory that's maximally simple or mathematical. So I'm saying mathematical simplicity seems to be a reasonably good guide for choosing the prior probabilities. But once the observations are taken into account with the likelihoods, then the highest posterior probabilities do not seem to go to the mathematically simplest theories. Well, the simplest mathematical theory I can think of is that nothing concrete exists, but that has zero likelihood. So it leads me to wonder, now this is where I'm going from cosmology from small c to cosmology with a big C. And then you might say I'm going beyond science, but it's sort of a similar line of reasoning. Is there another principle that works better for predicting or explaining the properties of the actual world? So conjectured principle is that the actual world is the best possible world. Well, you might laugh at that as Voltaire did. I think when I gave this argument to Stephen, he said, have you ever read Candide? Well, okay, I mean, Voltaire could make fun of it, but I don't think Leibniz's idea was wrong by such a simple, that you could ridicule, that you could really dismiss it by that sort of ridicule. Okay, let me explain what I mean by this and see where I'm thinking it might go to. So by the best possible world, I mean one with maximum value. I take value to be maximized to be the intrinsic value of conscious or sentient experiences. So experiences of pleasure, happiness, pleasure, joy, contentment, and satisfaction would have positive value. I'm having great positive value now, being in a wonderful place, seeing wonderful colleagues and friends, having the excitement of giving this talk. And, it's a very positive emotional experience. Then, conscious experiences of unhappiness, pain, agony, discontentment, and dissatisfaction would have negative value. Well, our universe seems to have enormous positive values, but it also seems to have enormous negative values. I've experienced a little bit of it, but other people far worse. I mean, it's hard for me even to imagine all the horror of the people who went through the Holocaust, for example. So it has horrible evil. Now, our universe also seems to have a very high degree of mathematical elegance and beauty. In some sense, it seems to be tipped more to the high end of the elegance than it is as far as the pleasure and pain part. So now we can partially appreciate the order, so that helps increase the value. But even I, as a physicist, I mean, I would prefer to give up, for me personally, I would prefer to give up the simple laws of physics if I could cure some friends with cancer. There's all sorts of things. If I could just perform magic, okay, then I'd have to say the law, whatever allowed that would mean the laws of physics aren't as simple. But, I personally would be happy to do that. So it seems like that intrinsic human value would be higher if disasters, disease, and cruelty were eliminated, even at the cost of less mathematical elegance for the laws of physics. So, okay, but now suppose you bring in the hypothesis that maybe there's a God. And suppose that this God appreciates that there's a sentient being. Well, first let's talk about a sentient being and then build up. Suppose there's a sentient being outside the universe that greatly appreciated this mathematical elegance. So that might, if it appreciated it enough, it might increase the value of the world to a maximum despite the sufferings within it. In other words, if more magic happened to reduce suffering here, it might make the universe sufficiently disordered that this being would be unhappy about that. So now this value might be maximized if this being had all possible knowledge, leading to the hypothesis of omniscience for full appreciation. It might also suggest the hypothesis that the being has omnipotence for actualizing the best possible world. And if the being actualized the world of maximum value, one might postulate the being as a creator and has omnibenevolence. He's really trying to make the whole world the best possible. So such an omniscient, omnipotent, omnibenevolent creator would fit the usual criteria for God. So thus the assumption the world is the maximum might suggest the conclusion of the existence of God. And since this is used as the optimal thing, I call it the optimal argument for the existence of God. So, in other words, without God, it would seem that the value of the universe could be increased by violation of the laws of physics, where whatever such violations would lead to more happiness than unhappiness. But with God, such violations might decrease God's happiness so much that the total value would be decreased. So perhaps the actual world does maximize the total value despite the suffering that are a consequence of these elegant laws. That I think, it's elegant laws that lead to cosmic rays and mutations and so on that come to cancer. I think they're a consequence of these elegant laws, in the quantum state. And I think God may grieve. I think he does grieve over the unpleasant consequences of the elegant laws, but it may be that inevitable trade-off. He's really trying to make things the best possible. So if God really does maximize the total value, he's doing what's best, and I don't think we can fault him. We may be selfish and say he should give our pleasure more importance than his, but why should that be? If he maximizes the total pleasure, the total happiness, and so on, that to me would seem to be best, and it seems unfair for us to demand that we ourselves should be treated better if it's a much greater expense to him. So now as a brief form of this, it is kind of tentative. I had a discussion just the last couple of days, even including last night, with a Christian philosopher back at Edmonton, and he said some original form where I didn't left out one was invalid, so I tried to make it a little more, it's a little convoluted, but let's see how we got here. So the first thing is that if there's one or more beings external to the universe exist who value the universe, one of them is God. Now, by this, I'm sort of eliminating the possibility that our universe is being simulated by some being. I mean, it may, if you didn't accept one, you could say, well, maybe the universe is being simulated by some beings and they get enormous pleasure out of it. And then the second thing is that if God exists, God loves elegant existence. He really loves elegance. And then three, the world is the best possible subject to two. In other words, if God doesn't exist, it's just the world is the best possible, according to this assumption. If God does exist, then it's the best possible subject to this part of the nature of God. And then four, the fact that the intrinsic value of our universe could have been higher. It's by itself isn't maximized. So then the point is, because of four, then three can't be true if there isn't, you know, some other being, if there isn't some value outside the universe that depends upon the universe. I mean, if it didn't depend on the universe, you could say, well, you just increase the universe's value and it has no effect in it. But if the value of the universe if the universe has an effect on the value of the external thing, then you could probably get around the contradiction between three and assuming there's no being outside. So then, therefore, you're led to the thing that this antecedent part of this must be true, and then if you accept this, that if such a being that does value it is God, then you're led to that, and then that gets you back to this one. So therefore, the idea is it's inconsistent. These assumptions are inconsistent if God doesn't exist, but they're consistent if God does exist, or they could be. There's no obvious reason why they're not consistent. So that's sort of a brief form of the argument, but I maybe value advice from philosophers to make it more precise. It's not. There's a bunch of probably unstated assumptions here that I have. Okay, so to conclude, I'm proposing that in a Bayesian analysis, that in which the probability of a particular observation is used as the likelihood of the theory, the sum of the probabilities of all observations should be unity. Not just the sum of the probability that the observation exists plus the probability that it doesn't exist. The probabilities of all observations. It seems plausible that you can find cosmological theories in which Boltzmann Brain that avoid Boltzmann Brain domination and explain the high order of our observation. And there's proposals out there, including some of my own, but none of them seem that elegant yet. So I don't think the major problem is yet solved. The next thing is the best theories don't seem to be the absolute simplest. So presumably something other than simplicity is maximized, such as value. And so the best explanation of the world may be that it's the best possible world. And then this assumption, along with the suitable assumptions about God's value, such as the love of mathematical elegance, leads to the optimal argument for the existence of God, that the world may maximize value only by including a God whose appreciation of the elegant universe and sentient beings he created overbalances the intrinsic sufferings within the universe. Okay, thanks.
Thank you, Don. So Don has illustrated the difference between cosmology with a big C and a small c. We've got a panel discussion coming up, so I'm afraid I'm only going to allow one question over there.
Well, I guess I'm saying that he appreciates that. I mean, it might be similar. Suppose I get aesthetic value from coming to this conference, and somebody says, well, aesthetic values don't mean anything. Therefore, if we use the money to come to this conference to do something else better, then, there's just no justification for us to have aesthetic value of coming to this conference, say. So, I mean, I think aesthetic value, if it's appreciated by conscious being, it's a real value that's really experienced. And so I'm just proposing that God he really does have this appreciation for the world. It's not just an abstract thing. It's a real appreciation for it.
Yeah, no, I just one thought. I understand
Okay.
that you could be an objectivist about the existence of aesthetic value in the world, and
Right.
To be conscious creatures that appreciate that value. But I'm having a hard time seeing how the appreciation of such value or the values themselves can serve as moral reasons.
Well, I guess I'm taking maybe a sort of pragmatist view that the best thing you could do is to try to maximize the value. And so I'm saying if God did the best he could do is to maximize the value, I think it should be the value of everything, of all possible value, including this aesthetic value. So I mean, if of course if you don't, if one doubted that there was real value there, then you could say what's the moral thing? But I mean I guess that's true. I mean if I'm going to deal with somebody in a moral way, I don't want to minimize, I don't want to reduce their value in any sense, but of course there's always trade-off. I mean, I have to provide for my family, and that may be a cost, well, I don't know. I mean, I get paid money through the university from the government, and you might say, well, maybe the government could have used this for some other thing. So there's always a trade-off. So I'm just saying that if there really is this trade-off, and it makes a really big difference to God, then it seems to be quite morally justified for God to make the choice that really does maximize the total value.